The response of single degree of freedom systems to harmonic excitation is a classical topic in structural dynamics, not only because such excitations are encountered in engineering systems, but also because understanding the response of structures to harmonic excitation provides insight into how the system will respond to other types of forces. A harmonic force P of t is simply the product of a scalar value P0 and a sine wave function. However, a cosine wave function can also be used. The sine wave is function of omega and time t, where P0 is the amplitude or maximum value of the force, and omega is the exciting frequency or forcing frequency. Omega defines the bandwidth of the sine wave function. As we all know, that omega capital T equals 2 pi, where capital T is the exciting period or forcing period. The figure shown on the top of the slide illustrates a harmonic force as function of T, where y-axis is the force value and x-axis is the time in seconds. Notice that the exciting frequency capital T is equal to 2 pi over omega, and the amplitude of the harmonic force is P0. The dashed line represents another harmonic force with a smaller exciting frequency and higher amplitude. The equation of motion can be expressed by the following equation, where m is the mass of the system or structure, u double dot of t is the acceleration as function of t, k is the stiffness of the system, u of t is the displacement or deformation of the system, and P0 sine omega t is the harmonic force. Notice that damping does not appear in the equation of motion since we are dealing with undamped system. The equation of motion is a second-order linear non-homogeneous differential equation. It can be shown that the particular solution to the differential equation can be expressed as where omega n is the natural circular frequency of the system. This solution is called the harmonic or forced vibration response. It can also be shown that the complementary solution to the differential equation can be expressed as the solution is called the free vibration response. The student can go back to any textbook in dynamics of structures to find the complete derivation of the particular and complementary solutions. The complete solution is the sum of the complementary and particular solutions. The complete solution can be expressed in terms of initial conditions, in other words, in terms of displacement at time 0 and velocity at time 0. The sine omega nt and cosine omega nt terms give an oscillation at the natural frequency of the system, while the sine omega t term gives an oscillation at the forcing or exciting frequency. The first of these is the free vibration or transient vibration, which depends on the initial displacement and velocity. The later is the forced vibration or steady-state vibration, which does not depend on the initial conditions. Since damping is inevitably present in real systems, free vibration decays and dies out with time. It is for this reason that this component is called a transient vibration. The figure shown on the top of the slide shows the response of undamped system to harmonic force for a specific condition. The solid line represents the total response, while the dashed line represents the steady-state response. The transient component is the difference between the solid and dashed lines, where it is seen to continue forever. When the initial conditions are zeros, in other words, when the displacement at time 0 equals 0 and the velocity at time 0 equals 0, the transient dynamic response can be expressed as: it can be concluded that 1. The transient vibration depends on the initial displacement and velocity. The transient vibration exists even if the initial conditions are zeros. Now let's investigate the steady-state dynamic response thoroughly. The static deformation U static of t is equal to P naught over K multiplied by sine omega t, where P naught over K is the maximum value of the static deformation and is denoted by U static naught. The steady-state dynamic response, which is a sinusoidal oscillation at the forcing frequency, may be expressed as: this equation may also be called the vibratory displacement. The student should always remember these two terminologies. 1. The static deformation, and 2. The maximum value of the static deformation. A graphical representation of 1 over 1 minus omega over omega n squared will help us to understand the physical meaning of this factor. Here, the y-axis is the factor under consideration, and the x-axis is the ratio of omega to omega n. Here, omega is the forcing frequency, and omega n is the natural circular frequency. When omega over omega n is less than 1, or omega is less than omega n, this factor is positive, indicating that the displacement u of t and the applied force p of t have the same algebraic sign. In other words, when the force acts to the right, the system would also be displaced to the right. The displacement is said to be in phase with the applied force. When omega over omega n is greater than 1, or omega is greater than omega n, this factor is negative, indicating that the displacement u of t and the applied force p of t have opposing algebraic signs. In other words, when the force acts to the right, the system would be displaced to the left. The displacement is said to be out of phase relative to the applied force. In this figure, I'm showing in-phase displacement and out-of-phase displacement graphically. Please pay attention to the direction of the applied force. In-phase displacement is in the same direction of the applied force, while out-of-phase displacement is in the opposite direction of the applied force. Equation 1, or the vibratory displacement u of t, can be rewritten in terms of the amplitude u0 and the phase angle phi. It can also be rewritten in terms of the maximum value of the static deformation u static naught, displacement response factor Rd, and the phase angle phi. Equating these two equations, we will get Rd equals these two phi's will adjust the algebraic sign of 1 over 1 minus omega over omega n squared, since absolute values have been used, so that Rd will always be positive. This figure shows the displacement response factor Rd versus the frequency ratio omega over omega n. If omega over omega n is small, in other words, the force is slowly varying, Rd is slightly larger than 1, and the amplitude of the dynamic deformation is essentially the same as the static deformation. If omega over omega n is greater than the square root of 2, in other words, omega is higher than the square root of 2 multiplied by omega n, Rd is smaller than 1, and the dynamic deformation amplitude is less than the static deformation. As omega over omega n increases beyond the square root of 2, Rd becomes smaller and approaches 0 as the ratio of omega to omega n approaches infinity, implying that the vibratory deformation due to a rapidly varying force is very small. If omega over omega n is close to 1, in other words, omega is close to omega n, Rd is many times larger than 1, implying that the deformation amplitude is much larger than the static deformation. If omega equals omega n, the system at resonance. The resonant frequency is defined as the forcing frequency at which Rd is maximum. For undamped system, the resonant frequency is omega n, and Rd is unbounded at this frequency. Resonant frequency of undamped system. The resonant frequency is defined as the forcing frequency at which Rd is maximum. For undamped system, the resonant frequency is omega n, and Rd is unbounded at this frequency. When omega equals omega n, the particular solution previously shown is no longer valid. It can be shown that the particular solution or the steady state response can be expressed as the complete solution for at rest initial conditions. In other words, when the initial displacement at times 0 equals the initial velocity at times 0, and both are 0, is the complete solution for at rest initial conditions can be rewritten as shown in equation 2a. The following figure shows the ratio of the complete displacement to the maximum static displacement versus T over Tn, where T is time and Tn is the natural period. It can be seen that the vibratory deformation does not become unbounded immediately, but gradually and the time taken to complete one cycle of vibration is Tn. Moreover, in each cycle, the deformation amplitude increases by pi multiplied by p0 over k. This is an academic result and should be interpreted appropriately for real structures. As the deformation continues to increase, at some point in time, the system would fail if it's brittle. On the other hand, the system would yield if it's ductile, its stiffness would decrease, and its natural frequency would no longer be equal to the forcing frequency, and equation 2, or previous figure, would no longer be valid. Harmonic vibration of damped systems. For damped systems, the equation of motion can be written as where C is the damping coefficient and U dot of T is the velocity of the system. If the displacement at time 0 is U of 0 and the velocity at time 0 is U dot of 0, it can be shown that the particular solution is C times sine omega t plus D times cosine omega t, where C is equal to and D is equal to. It can also be shown that the complementary solution is where zeta is the damping ratio and omega d is the natural frequency of damped vibration. The relationship between omega d and omega n is shown as follows. The complete solution is the sum of the particular solution and the complementary solution. The complete solution consists of two parts: the transient vibration or free vibration and the steady state vibration or forced vibration. The following figure shows the total response and the steady state response. Here, y-axis is the ratio of the complete displacement to the maximum static displacement, and x-axis is t over t. The difference between the two is the free response, which decays exponentially with time at a rate depending on omega over omega n and zeta. Eventually, the free response becomes negligible, hence we call it transient response, while the forced response remains, and therefore we call it steady state response. For the rest of this chapter, we will be focusing on the steady state response. It should be recognized that the largest deformation peak may occur before the system has reached the steady state. Response for omega equals omega n, where omega is the forcing frequency and omega n is the natural circular frequency. For omega equals omega n, C equals 0 and D equals. For omega equals omega n and 0 initial conditions, A and B can be expressed as the total displacement becomes, for lightly damped systems, in other words, zeta is very small, the sinusoidal term in the above equation is small, and omega d approximately equals omega n. Therefore, the total displacement can be expressed as Please pay attention to the envelope function. The first figure on this slide shows the response of damped system with damping ratio zeta equals 5%, omega equals omega n, and at rest initial conditions. This is a graphical representation of the last equation found on the previous slide. It can be seen that the envelope curve is an exponential function and the amplitude of the steady state response is 1/2 zeta. The second figure shows the response of three systems. Zeta equals 1%, 5%, and 10%. Omega equals omega n, and at rest initial conditions. Notice that the steady state amplitude gets smaller as the damping ratio zeta gets larger. Recall that omega n equals 2 pi over Tn, where Tn is the natural period. If T equals J times Tn, where J is the number of cycles of harmonic force, U0 equals the maximum static deformation divided by 2 zeta, Tn equals 2 pi over omega n, and setting cosine omega nt to 1, the previously obtained function shown on the top right corner of the slide can be rewritten as the figure on this slide shows the variation of response amplitude with number of cycles of harmonic force with the frequency omega equals omega n. It can be seen that the lighter the damping, the larger is the number of cycles required to reach a certain percentage of U0, the steady state amplitude. For example, the number of cycles required to reach 95% of U0 is 48 for zeta equals 1%, 24 for zeta equals 2%, 10 for zeta equals 5%, 5 for zeta equals 10%, and 2 for zeta equals 20%. Maximum deformation and phase lag phi. The steady state deformation of the system due to harmonic force can be rewritten as function of phase angle phi, as shown in this equation, where U0 is the amplitude of the steady state deformation, Rd is the deformation response factor, and phi is the phase angle. It can be shown that U0 equals the square root of c squared plus d squared, and phi equals tan inverse of negative d over c. C and d have already been calculated previously. It can also be shown from this equation that Rd equals U0 over U static node, and remember, U static node is the maximum static deformation, equals 1 over this term. The following figure shows the steady state response of damped systems when zeta equals 0.2 to sinusoidal force for 3 values of the frequency ratio omega over omega n. A, omega over omega n equals 0.5, B, omega over omega n equals 1, and C, omega over omega n equals 2. These figures are based on the following equation. The following figure shows the deformation response factor and phase angle for a damped system excited by harmonic force. The figure is based on this equation. If the frequency ratio is much less than 1, in other words, T is much greater than Tn, implying that the force is slowly varying, Rd is only slightly larger than 1 and is independent of damping. The result implies that the amplitude of dynamic response is the same as the static deformation and is controlled by the stiffness of the system. If omega over omega n is much greater than 1, in other words, T is much less than Tn, implying that the force is rapidly varying, Rd approaches 0 as omega over omega n increases and is unaffected by damping. For larger values of omega over omega n, the term omega over omega n to power 4 is dominant. The result implies that the response is controlled by the mass of the system. If omega over omega n is approximately equal to 1, in other words, the forcing frequency is close to the natural frequency of the system, Rd is very sensitive to damping, and for the smaller damping values, Rd can be several times larger than 1, implying that the amplitude of dynamic response can be much larger than the static deformation. The result implies that the response is controlled by the damping of the system. If omega over omega n is much less than 1, in other words, the force is slowly varying, phi is close to 0 degrees, and the displacement is in phase with the applied force. When the force acts to the right, the system would also displace to the right. If omega over omega n is much greater than 1, in other words, the force is rapidly varying, phi is close to 180 degrees, and the displacement is out of phase relative to the applied force. When the force acts to the right, the system would be displaced to the left. If omega over omega n equals 1, in other words, the forcing frequency is equal to the natural frequency, phi equals 90 degrees for all values of zeta, and the displacement attains its peaks when the force passes through zeros. Dynamic response factors for steady-state response. It has already been showed that the deformation response factor, Rd, is equal to U0 over U static naught, where U0 is the amplitude of the steady-state deformation and U static naught is the maximum static deformation. Taking the first and second derivatives of the steady-state deformation with respect to time t, making suitable substitutions and rearranging the terms, we can obtain the velocity response factor Rv and the acceleration response factor Ra. The simple relations among the dynamic response factors make it possible to present all three factors in a single graph. Please note that the words deformation and displacement have been used interchangeably in this course. Please remember that the steady-state deformation can be expressed as: now, by taking the first derivative of the steady-state deformation with respect to time t, we will get the steady-state velocity. And the amplitude of the steady-state velocity can be expressed as: taking the second derivative of the steady-state deformation with respect to time t, we will get the steady-state acceleration. and the amplitude of the steady state acceleration can be expressed as the following figure shows the deformation, velocity, and acceleration response factors for a damped system excited by harmonic force. The deformation response factor Rd is unity at omega over omega n equals 0. Peaks at omega over omega n is less than 1 and approaches 0 as omega over omega n approaches infinity. The velocity response factor Rv is 0 at omega over omega n equals 0, peaks at omega over omega n equals 1, and approaches 0 as omega over omega n approaches infinity. The acceleration response factor Ra is 0 at omega over omega n equals 0, peaks at omega over omega n is greater than 1, and approaches unity as omega over omega n approaches infinity. For zeta greater than 1 over the square root of 2, no peak occurs for Rd and Ra. The following figure shows a four-way logarithmic plot of deformation, velocity, and acceleration response factors for a damped system excited by harmonic force. Resonant frequencies and resonant responses. Before we start off with this topic, we need to memorize the simple relations among the three dynamic response factors and define our objective. The objective here is to determine the largest response amplitude of the dynamic response factor. A resonant frequency is defined as the forcing frequency at which the largest response amplitude occurs. Taking the first derivative of the steady state deformation with respect to the ratio omega over omega n, equating the new equation to 0, we can get omega that causes the largest deformation response amplitude, which is called displacement resonant frequency. Now, if we substitute the displacement response frequency into the steady state deformation, we can get the largest response amplitude. Taking the first derivative of the steady state velocity with respect to the ratio omega over omega n, equating the new equation to 0, we can get omega that causes the largest velocity response amplitude, which is called velocity resonant frequency. Now, if we substitute the velocity resonant frequency into the steady state velocity, we can get the largest response amplitude. In a similar manner, we can find the largest response amplitude of the steady state acceleration. Half-power bandwidth. An important property of the frequency response curve for Rd is the half-power bandwidth. The following figure shows the definition of half-power bandwidth. If omega A and omega B are the forcing frequencies on either side of the resonant frequency, at which the amplitude is 1 over the square root of 2 times the resonant amplitude, then for small zeta, we have omega b minus omega a over omega n equals to zeta. Therefore, zeta can be written as omega b minus omega a, the whole thing, over 2 omega n. This equation can also be rewritten as zeta equals Fb minus Fa, the whole thing over 2Fn, where F is the cyclic frequency of the harmonic force, Fn is the natural cyclic frequency of the system. Force transmission and vibration isolation. The mass spring damper system shown is subjected to a harmonic force P over T. The force transmitted to the base Ft is Fs plus Fd. It can also be expressed as K times U of T plus C times U dot of T, where Fs is the elastic resisting force, Fd is the damping resisting force, K is the stiffness of the spring, and C is the damping coefficient of the damper. If we substitute the steady-state deformation, the first derivative of the steady-state deformation with respect to time, the maximum static deformation, and damping coefficient into the equation of transmitted force, we will get the following equation. It can easily be shown that the amplitude of the transmitted force equation is, substituting for Rd gives an equation for the ratio of the maximum transmitted force to the amplitude P0 of the applied force. This ratio is known as the transmissibility of the system Tr. The following figure shows the force transmissibility versus the ratio omega over omega n. It can be observed that damping decreases the transmitted force only if omega over omega n is less than the square root of 2. For the transmitted force to be less than the applied force, in other words, Tr is less than 1, the natural frequency should be small enough so that omega over omega n is greater than the square root of 2. Since natural frequency and stiffness of the support system are proportional, the stiffness of the support system should also be small. In this frequency range, no damping is desired in the support system because damping increases the transmitted force. This implies a trade-off between a soft spring to reduce the transmitted force and an acceptable static displacement. Response to ground motion and vibration isolation. As previously mentioned, the particular solution to the equation of motion of damped system under harmonic force is C times sine omega t plus D times cosine omega t. The equation of motion of damped system under earthquake excitation is similar to the equation of motion of damped system under harmonic force, with exception that the term P0 sine omega t should be replaced with this term, where m is the mass of the system and u double dot g of t is the ground acceleration. The ground acceleration is the ground acceleration amplitude times sine omega t. Please check chapter 1. The solution to this differential equation is: what does this displacement represent? From chapter 1, we have learned that there are 3 types of displacements associated with earthquake excitation. The displacement of the ground, and is denoted by U ground. The total displacement or absolute displacement of the mass, and is denoted by U T. And the relative displacement between the mass and the ground, and is denoted by U. Therefore, the above solution represents the relative displacement between the mass and ground. The corresponding total or absolute acceleration is given as where u double dot g of t equals u double dot g naught times sine omega t, and u double dot of t is the second derivative of u of t. It can be shown that ground motion transmissibility is identical to force transmissibility, where u double dot g naught t is the acceleration amplitude. Finally, if the ground motion is defined as ug of t equals ug naught sine omega t, it can be shown that the amplitude u naught t of the total displacement ut of t of the mass is given by this figure shows the ground motion as function of distance x. One more thing before we finish up this presentation. The student should keep in mind that velocity equals time multiplied by distance. Please note that a new presentation that contains the derivation of some of the equations used in this presentation, 7 solved examples, and some miscellaneous topics found in Chapter 3 will be uploaded soon.